All right, get going here. This thing is still here. Obviously need a bigger green screen than the size that's in here. Just this was sort of a playground thing. So anyways, new toy, all the pen tablet stuff. So I want to go through two circuit solutions, two different kinds of circuit solutions. The first one's going to be the easy thing, which is a reduction of a circuit. So we can reduce this circuit down to an equivalent resistor, okay? And get the total current in the circuit, and then we can work our way back. And that's one approach to solving a circuit. Inevitably, you always do that on some level when you're solving a circuit. We're doing in an introductory course the kind of lowest level of circuit analysis, just using Kirchhoff's loop and node rules. The next layer up would be something called mesh analysis. So those of you that are in or will be in circuits, you'll learn that. There's Thevenin's theorem and stuff. There are a number of more advanced and in some ways better, more efficient ways to solve circuits. And since this is physics, we got to keep it as basic. Since it's introductory physics, we got to keep it as basic as we can. So I'm not gonna teach you mesh analysis. All right, but here's this circuit, which if I were to draw it, which you can sort of do if you just switch it into this mode. All right, you don't have to build this circuit, but if I were to draw this circuit, I would have, and it's important to know which way your battery is facing. The big dash is your positive terminal. And so more on that later in the textbook. So we would have this circuit would be drawn as such, and then repeating that down below. So being pretty lazy with my resistor squiggles, if you will. So we would have some voltage up here. If we were to call this R1, actually, let me and then the same down here. So these parallel branches are identical to one another. And we could have three different resistor values. I guess we could let them all equal each other too, but just making that distinction. And so this circuit can be reduced. And so if you take a look at, this parallel branch, right, or this parallel network, this sub-network, if you will. There's four of them. There are three more of them, and this could be reduced to a single resistor, okay? And so 1 over what I'll call R12, which would be the equivalent resistance. So a lot of textbooks will, the equivalent resistance of this parallel or even a series branch, you might write R sub EQ, but I'm going to be more explicit because I'm going to condense this whole branch that it's on into one resistor, which means the other one is identical, and then those are two equivalent resistances in parallel, and you would go through the motions one more time. And so to use the rule that the textbook and videos have shown, I would have 1 over R1 plus 1 over R2, which means that R12, the equivalent resistance, will be the product over the sum. And you can just sort of always go there when it's just a simple 2 resistors in parallel. It's always going to be the product over the sum. And if it's 3 in parallel, it's still going to be products over sums, but it'll be a more complicated fraction solution, rational equation, if you will. All right. And so we could compute that if we knew the values, and I'm going to save that for a different time. And scroll this up here. So now I'm going to reduce this circuit. I'm going to redraw it. And so now I'll have, the battery didn't change. Okay. Still V, but now I'll have an equivalent resistance. I'll have R12, R3, and R12, and then likewise, parallel to that. And so we've reduced that circuit by just applying this parallel resistance computation rule, which comes from conserving energy ultimately. And there you go. So it's a simpler circuit. I could take out that parallel part and replace it with a resistor, a single resistor, and now I have I still have a series parallel because the parallel branches have series components. Well, the series resistance is a piece of cake. If I wanted to get an equivalent resistance of this part right here, well then my R123, which would be including the R12s and the 3, would just be the sum. It would be 2 R12s plus an R3, because there's 2 of the same thing. And I could have one more circuit reduction, well, next to the last one, where we have still have V, R1, 2, 3, and R, whoops, 1, 2, 3. And then the final, so these are in parallel. So we go back to our parallel stuff. So total resistance. And so when you get to the last step, you would just call that R usually. It's your total resistance. You could say R subtotal if you wanted. I'm just going to no subscript, meaning the final total amount or whatever. And again, since it's 2 identical resistors in parallel, you know that it's the product over the sum, which would be more simply written as that squared over to R123. And so now I have 3 formulas for this circuit. Okay, and maybe we try to get it all together. You can see the progression of taking the full circuit, doing equivalent resistance maneuvers, and you get down to the end here, the total resistance. So now that I have a total resistance, when you write Ohm's law, you're assuming, the assumption is that these are all the total amounts that this and this are our total whatevers. That's the fundamental assumption that you would make. And so if the total resistance is R, and I could compute that, but I'd have to go back and get all the other ones. So I would need to compute R12, put that forward into the R123 equation with R3, and then so forth, so on. So let's do that. All right. So R12 will be R1 times R2 over their sum, which is going to be, I have a 3 and a 6, and I actually meant to have this be 20. So I'm consistent with my notes, won't really change much as far as the unvalued equations go, just the symbolic version. All right, so there we go. That's closer to what I was all scribbling. And so I have a 3 times 6 over 3 plus 6. So that's not terribly difficult thing there. So R12 would be equal to 2 ohms. All right. So then I would pass that forward. Meant to use blue, but forgot. So R123, that equivalent resistance is 2R12 plus R3, which is 2 times 2 plus 20, which is 24 ohms. And then that would mean that finally our R value, total resistance, would be R1. I guess I could have it should have earlier. This will just be R123 over 2, which makes sense. In fact, every time you have two resistors in parallel that are identical, their equivalent resistance is always half of one of them. That trivial mathematical thing there. And so this means that R is just going to be 12. So 12 ohms is the total resistance of the circuit. And that means, since I know voltage and now the total resistance of the circuit, I can know the total amps of the circuit, which is very simple in this case. So V equals IR implies that I equals V over R, which is 12 volts over 12 ohms, which equals 1 amp, which is exactly what we have on screen here in the simulation for that circuit. So that's a good thing. It's always good when the professor gets it right. And of course it was set up and tested in advance, but it's simple math. This is algebra and circuit analysis. Well, everything you're doing in science engineering inevitably involves some amount of algebra. So there you go. We have a solution. We could go back and figure out other values in the circuit. So for example, what if we were to what is the voltage across resistor 3? So when I write V3, I mean what would be the voltage here. That's what the voltage drop across that 20 ohm resistor. All right, so that's the assumption, which would mean you would want to know I 3, R3. Okay, so we can look at this and see what the current going through that resistor is. It's 0.5 amp. Okay, which is just the sum of the other two, you know, right here. I don't know if you can. Yeah, there's a dot on my tablet screen, but not on the others. But get my mouse here. So right here, those two just add up to the 0.5. Okay, so simple stuff. If we were to bust out this voltmeter, we could measure it, get our 10-volt drop across that. So that means that the other two branches just have a 1-volt drop. They're identical little parallel networks, and so there must be split evenly the rest of the way. So that's one. The main thing here wasn't so much as going back and using Ohm's law on the little pieces of the circuit. That's sort of trivial, but just the reduction itself, and that right there. So this is on video, and I should be able to send the PDF out later. I'll just leave that there. So that's a circuit reduction, one of the important skills that you would have in this circuit analysis game. All right, so now let's get to a slightly more complicated circuit analysis thing. So I want to give you already have 1 or 2 examples of what's going to be on your test next week, your first celebration of knowledge in this circuit game, or first major celebration of knowledge. And I just want to throw another twist into that. And you hopefully are recognizing that the circuit that I'm about to build is fundamentally the same as the one that's been lectured on already. And it's also fundamentally the same as the one you're going to be tested on. Just some small differences in that. So actually I want to put some ammeters in here. So build this circuit. Put one in there too. Wish they had a vertical version already queued up, but they don't. All right. So just going to be a simple one. Verify. Yeah, it's just those 3 in parallel. All right, and I'm going to leave them and let's do, I'll keep them, actually I'll keep both of these at 9 volts. So what I want to do here is solve this using the Kirchhoffs rules. And what we're going to do, so I want to demonstrate again, do the node and the loop equations, get a system of equations that's sufficient for getting a solution, which means you have the same number of equations as you have on nodes. Once you have that, you can stop. And in fact, in this circuit, we'll do one more loop than is necessary because I want to point out why the third loop equation is not useful to us. And so sometimes you'll just keep doing work and it's not useful work, at least practically speaking. It might be useful on an academic level, but not in any other way. So I'm going to stretch this out a little bit since I can for this circuit. So simple circuit, identical batteries, identical resistors, simple node situation. But let's draw our diagram here. Let me get this out of the way. So we have one battery going into a node there, another battery. And we could call this R1, R2, R3. We call this V1. In fact, instead of V1, I'm going to call it, I'm going to use those textbook conventions for big fancy epsilon for representing electromotive force, which is a shift in jargon. It's still a voltage, it's still a battery, okay? And just for clarity, you know, this is the positive end of battery, negative, positive end, negative. So here's what we do. And I was telling you about, you know, the assumptions you make about current flow. I am going to pitch this in terms of electron flow. And so electrons would want to get away from the negative pole of this battery and come back around to the positive pole. So that means under that viewpoint, current would be flowing out of the batteries this way, which is exactly what I see on screen. So when you get to your test next week, you can obviously do the same thing I'm doing right now. Know in advance what the current flows are, and your assumption will be that. Your equations are going to give you conventional current flow answers, which is the opposite direction. So conventional current flow is the opposite direction as electron current flow, but it is in the direction of the electric field. That's the current density, if you will, which is a thing you have to kind of read and ponder a little bit. So if the currents are coming into this node here, which we call this node A, call this node B, then there's going to be some upward flow there. And this is a relatively simple thing to do here. Now, here's the thing that can get irritating if you don't think it through in advance, is if you were to first decide that, say, this down here was going to be current 1 because it's coming out of battery 1, then you're going to have some subscript confusion, all right? And when you can, and you always can, I would recommend that you call the current going through a resistor, you subscript it the same way as that resistor. More complicated circuits means that won't always match up. Like if I had another resistor in series with it, you know, you'd have to pick one. So I'm going to call this I2, okay? And we could say that I2 going through resistor 2 is going that direction. All right, and that means that it's going to come up to this node and split off in those directions, which means the current going through resistor 1 I can call I1, the current going through resistor 3 I can call I3, okay? Which means I1 is coming through battery 1, and I3 is coming through battery 2. And so you need to pin these things down and track with that. So I can write a node equation. Let's do this. The node rules, okay? For A, I'm going to have I1 plus I3 equals I2. And for B, I'm going to have the reverse, I1 plus I3. You know, 6 and 1/2 does the other, they're the same statement, just you're being explicit with the rules. Do you have to write both in this case? No. If there was another layer like we had, I think the one you have has a top layer to it, then it would be worth writing that node probably. Or as many nodes as you have, generally speaking, they're worth writing the equation for that node down, especially as you've had 3, 4, 5 times the nodes, you obviously would want to do that. All right, so the next thing that we would do would be our loop rule. All right, so switch colors up there. So the loop rule, you have choices. You could always go the same direction from a point, or you could go opposite directions, as long as you are consistent and correct with the way you traverse resistors and voltage sources when you take that loop. So I am going to center everything on position A. And so I'm going to call loop 1 that traversing of the circuit. And so that's a clockwise. And then I'm going to go counterclockwise for my loop 2. And then for my loop 3, I'm going to go all the way around in a clockwise fashion. And that will be my loop 3 traversing. So these are identical to what you can see in the book. The book images are a bit cleaner because it's a perfectly created little graphic, actually written in code. It's not actually something a graphic artist would do, unless they happen to be using the code that goes into writing math and science textbooks and papers. Some of you will have to learn LaTeX to do the stuff you do. All right, so let's get these loop rules going. So loop 1, in fact, I'm going to remove that just so that there's less to look at as we go. So loop 1, my loop 1 equation. Okay, so what am I going to have? So loop 1, the first thing I go through is the battery. And notice I'm going from plus to minus. I'm going uphill through the battery. So that's a positive voltage. So I would just write E1. Then as I traverse through resistor 1 here, I'm going kind of against the flow because I am assuming that current 1 is going downward, electron flow is going downward. I'm traversing its change in electric potential I'm going uphill again, metaphorically, because I'm going against the stream. Okay, so that's going to be a plus. And so and remember the loop rules are we're really doing V equals IR. Okay, they're voltage chunks. And so we're really writing an IR. So this is going to be R1, I1. And the reason I'm going to put it in that order is your resistance values tend to be known. And so you have a number coefficient on the thing you're going to solve for, current. All right. And then as we come around the bin, we're also going the opposite way of current flow, of electron flow through that resistor. So I'm going to have an R2, I2, and then I get back to my node, my starting point. According to conservation of energy, which is all that Kirchhoff's rules are, I have completed the loop, and all those things should add up to 0. Okay, in that regard. So we have this loop equation. So now if I were to do loop 2, I'll just write it. So I'm going uphill again through that battery, and then going against the flow again. So R3, I3, and then plus R2, I2. Okay, so at this point, you could stop with your loop equations because I have, and we're going to know the resistance values because we can look at them. They're all 10. We know the voltage values. They're both 9. Okay, so if we just look at this, this is an equation that has 1, 2, 3. This one has 1 and 2, and this one has 3. Yay. That's really all you need to have your system of equations. However, I'm going to do what was promised because it's worth doing from just a pure academic viewpoint. Loop 3 would be, again, an uphill through, so it's going to be just like loop 1 initially, and then it's going to be just like, well, not just like loop 2 because loop 2 is going the other direction. I'm going to have, when I come around the bend here to R3, going in the same direction. So now I'm going to have a minus R3, I3, and since I'm going downhill through the battery, positive to negative, that's going to be a minus E2. If you think about it, the loop 3 equation is just the difference between loop 1 and 2. So it's a redundant equation, and the more experienced you are as a circuit analyzer, the more quickly you would see the uselessness of doing loop 3. I point this out just to make that mathematical fact explicit, but also to bring you back to what's highlighted in cyan, the 1, 2s, and 3s. As soon as you have the same number of unknowns as you have equations spread out, then you're ready to go. And so whether you do it by hand or by a computer, that's the next piece of the puzzle. And the problem, I wish Mathway would accept subscripted variables. You can type them in, but I can't get it to give me a solution the way that we would write it in physics. And so I have to kind of redo this these equations. And so my A equation would need to be x plus z equals y. Just if 1, 2, and 3 are going to be x, y, z, I could do ABCs, whatever 3 letters you want to choose. My loop 1 equation will be 9 plus 10x plus 10y equals 0. Or we could write it probably what would be slicker would be to just write 10x plus 10y is minus 9. Is it x and y? Yes. And loop 2 will have the same basic structure, except it's y and z, because you have the 2 and 3 subscripts. So 10y plus 10z equals a negative 9. So if we were to take this And this, we could have our kind of classical algebra version of that, and we could come over to Mathway. Or some similar tool, whatever floats your boat. And we could type these in. X plus y equals z, comma, 10x plus 10y equals minus 9. And 10y plus 10z equals minus 9. Solve the system of equations. Did I, is that my all 10s? Oh, I have that equation wrong. No wonder I get the wrong answer. It's not x plus y equals z. It's x plus z. Y equals x plus z. That didn't work like, there you go. All right, so you can see 3/10 and 3/5 as answers. So 3/10 will be 0.33, 3/5 will be 0.6, which is exactly, or sorry, 3/10, yeah, so 0.3, not 1/3 would be 0.33. I need more coffee. I only had my one this morning. So you can see that we get that was almost a good maneuver there. Where did there we go. So that set of equations matches that circuit and this analysis here. So you can sort of see it all at once here in that regard. So my recommendation to you is do the physics part. So it's been a while since we've done the physics is done, PID. That was, mid semester, last semester, we sort of were done with that. But the physics would be done up here with the loop equations. Once you have those loop equations, you fundamentally have the answer because it's just a math maneuver after that. All right. And so the trouble is that for certain computational tools that would do the math for you, you'd have to alter them like we did. One of the things you can do, let's say you needed to solve multiple, like you wanted to change things up, okay? You could, instead of having number coefficients, you could pick something like, I'll have n, or let's do this, a and b for x and y. Instead of a particular number, we could put n in here. So y would have a b coefficient on it. Z would, like have a c coefficient. And instead of -9, we could have the other value. And then what you could do is say a equals 10, b equals 10, just to keep it like it was, c equals 10, and then you would say probably what would be better if you're going to do this is to leave it like it was originally before we simplified it. That way you could just enter the raw values and this better work like it did last time. I did this earlier just to make sure it worked, and you get the same answers. So now what you could do is you could come over here and change the circuit, okay? Or you could say, okay, if I click on that again and say, what happens if A is 5, B is 7, leave that alone, and let's make the right battery 12. It'll give us a new set of answers, and then we could go over here and go, all right, let's make this 5. Let's make this 7, yeah. And this battery 12. So now we have questionable answers. Didn't bring a calculator, but minus 10/9, that should be bigger than 1. And I don't see a bigger than 1 current on here. Well, it was working unless I misentered something. Doesn't look like I did. Anyways, that's that. I just wanted to give you that breakdown of the thing. Probably just enter it, you know, as it is, like we showed first, because really you only have one to solve for, so it's not like you need it to be variable for anything you throw at it. But I am puzzled why it was given some not entirely correct numbers there, or any of them right. I must have entered something wrong. 31. Yeah, none of those are right. That's interesting. Must have done my, oh, there it is. I got a wrong coefficient. So A's are on X, B's are on Y, C are on Z. Okay, that's better because now they're all less than 1. So it's way more believable. So let's say 69 divided by 155 is 0.45. So yeah, it does work. Good save, Angular. All right, so that is it. I just wanted you to have another example walkthrough of doing all this. Okay, taking a circuit that needs to be solved with Kirchhoff's rules and going through those motions. And if you want to solve it by hand, go for it. I recommend you use your calculator, computer, and just all you got to say, you know, Mathway says, show a screenshot if you want, and that's it. So I will end the recording there.